gentlemen. Today we're talking about section 4.7, which is using isosceles and equilateral triangles. And we're going to start by looking at a theorem which is called the base angles theorem, which we've talked about in class. But I'm going to show you the proof of this theorem because, again, theorems always have proofs. So we're given the fact that these two sides are congruent. We want to prove that these two angles are. So to do that, we're going to start, first of all, by making a point M. And we're going to say that M is the midpoint of that bottom segment, using our definition of a midpoint. We're going to put it right in the middle. Yes, you can add new things to a picture as long as you use the correct, definition. So, that being said, what we'll also do is we're going to draw segment JM, which will go from the top corner up at J to point M at the bottom. And our reason for that will be postulate 5, which states through any 2 points, there exists exactly one line. So through point J and point M, we'll draw that exactly one line, the only line that is possible. So now we have two triangles, and we can prove these two triangles congruent and say the corresponding pieces are, so we can say that these two angles are congruent. So we're going to use something to prove those two triangles are. So from this point, we can say that MK is congruent to ML, these two segments, because the definition of a midpoint. We made sure that M was the midpoint, so we can say these two segments are congruent. Next, these two triangles share a side. Oops, I'm sorry. We're given these two sides are congruent, and then they also share a side using our reflexive property. And so we can say the two triangles are congruent using our side-side-side congruence postulate. And since the two triangles are congruent, we can say that the two angles will be congruent using our corresponding, corresponding angles of congruent triangles are congruent. So again, we added some things to the picture so we could use them in our proof. But we had to prove these two triangles were, so we can say the two angles were. And that's kind of the summary of the proof of the base angles theorem. That's why it works, because again, if it's there's a theorem, there's always a proof. So let's go ahead and use this theorem. What we can do is you apply it to isosceles triangles in general. If we have two sides are congruent and the angles across from them are. So in this case, if we know that HG is congruent to HK, then what we can conclude is that the angles across from them are congruent. So we can say that angle G, I can't say angle K because I have two angles here, so I have to use 3 letters. So I'll use 3 letters for both. I'll say H, G, and K. That angle is congruent to H, K, G. And that's just a quick example of how we can use the theorem. We can also use the converse of the theorem, which is the theorem in itself, which there's a proof for that, but I'm not going to go into that today. But the converse is also true. If we have two angles congruent like these two, then we know the sides across from them are congruent as well. So here we can say that HK is congruent to JK because the angles across from them are congruent, so the sides are. So either way it works. Again, that's the base angles theorem for this one, and this was the base angles theorem converse. Let's apply it to an equilateral triangle, because an equilateral triangle is a special type of isosceles triangle. A isosceles triangle is any triangle with at least 2 congruent sides. Well, if it's equilateral, it does have at least 2 congruent sides. It has 3. So in this case, if these 3 sides are congruent, then all of the angles across from them are congruent as well. And we know that all 3 angles should add to give us 180. So I'm going to call all of these x because they're all equal to each other. They're all the same. So if I add my x's together, it should equal 180. And combining like terms, this should be 3x equals 180. Dividing by 3, x is 60. So that means that all 3 of my angles are going to equal 60 degrees. The measure of angle P, the measure of angle Q, and the measure of angle R are all 60 degrees. And that's actually true for all equilateral or equiangular triangles. If it's equilateral, it will always be equiangular because of the base angles theorem. In general, with the base angles theorem, the reason why we call it base angles is the two angles that are congruent to each other are considered our base angles. The remaining angle is called our vertex angle. So just a little bit of vocabulary I neglected to mention earlier. Let's move on to another example. We'll do this one here and we'll call it a day because these are the ones we went over in class. So find the values of x and y in the diagram. Well, in this case, this is an equilateral triangle, so I know all three of these angles are congruent. I also know that these two base angles are congruent, so these two sides will be. So I have all these sides that are the same measure. So solving for x, I know that x plus 1 and 4 should be congruent because they have the same number of tick marks. How does that work logically? Well, we know that all three of these sides are congruent, and these two sides are congruent. So by the transitive property, these two sides will be congruent as well, cutting out the shared piece, the middle piece here. So if I subtract 1 from both sides, x is 3. And for y, I know y is going to be 4 because this is equilateral, so if this is 4, so is y. So there's an example where you have two triangles combined into one, where you have to use both triangles to solve for both variables. So that's kind of a brief overview of section 4.7. I hope this video is helpful. I hope it was a nice break and proof for you.